The PathwayBench research paper presents a novel benchmark for assessing the routability of pedestrian pathway networks inferred from multi-city imagery. This benchmark addresses the challenges of extracting accurate, routable paths from remote sensing inputs, particularly for pedestrian paths that are narrower, more frequently disconnected, and variable in smaller areas compared to roads. The dataset includes regions from 3 cities, featuring co-registered aerial imagery, road networks, and human-validated pedestrian pathways. The evaluation procedure emphasizes graph connectivity and introduces a new metric of local traversability as an efficient proxy for global graph routability, focusing on the traveler experience. This approach surfaces strengths and weaknesses of existing methods that are hidden by simple edge-counting metrics over single-region datasets. The paper contributes a human-validated ground truth pathway graph, evaluation criteria emphasizing graph connectivity, and an evaluation of state-of-the-art methods for the pedestrian pathway extraction problem, demonstrating the exposure of unique challenges and quality issues that correlate with downstream utility. The research paper discusses the need for a standard dataset and benchmark for pedestrian pathway graph mapping. The authors survey related work in 3 domains: street and road network mapping, methods to map pedestrian environments, and available remote sensing datasets. They highlight the limitations of existing studies, which primarily focus on automobile road detection and extraction, neglecting the pedestrian environment. The authors note that few studies have addressed pedestrian environment mapping, and those that have often require physical systems to cover a large area or rely on incomplete information. They also discuss the challenges of feature detection from satellite imagery, such as vegetation obstructions, and the difficulties in correctly representing path connectivity and routability. To address these limitations, the authors introduce the PathwayBench dataset, which provides annotations of connected, annotated pedestrian path networks represented as graphs, along with co-registered aerial imagery, annotated road networks, and rasterized street maps as input features. The dataset covers select regions in 3 U.S. cities and additional cities in North and South America. The graph annotations for pedestrian pathways are represented in GeoJSON format and were collected and annotated through a standardized process involving city agencies and crowdsourcing platforms like OpenStreetMap. Each dataset sample includes aerial imagery, road network, rasterized street map tiles, human-validated pedestrian pathway graph, and rasterized pathways for supporting segmentation methods. The PathwayBench dataset also provides semantic segmentation annotations for 3 distinct classes: corner bulbs, sidewalks, and crossings. These classes are essential for semantically segmenting the pedestrian environment, and the dataset is designed to be balanced and representative, including images from both North and South American urban contexts. However, the authors acknowledge the challenge of lower-resolution aerial satellite images available for South American cities. Overall, the PathwayBench dataset aims to provide a comprehensive and standardized benchmark for pedestrian pathway graph mapping, addressing the limitations of existing datasets and methods. The research focuses on improving the accuracy of pedestrian pathway graphs by leveraging multiple sources of data and novel metrics for evaluation. It begins by introducing the PathwayBench dataset, which offers diverse imagery and annotations from various geographic areas. The dataset includes aerial images, street maps, and pathway graphs, highlighting the challenges of occlusion and the importance of using multiple sources for better segmentation outcomes. The concept of routability is then discussed, emphasizing the need for measuring local and global routability. Local routability is evaluated through polygon-based metrics, such as degree centrality, betweenus centrality, and traversability, which assess the ability to travel through small intersection-scale regions. Traversability is a novel metric that measures the ability to navigate from one boundary of a polygon to another, favoring global routability over local variations. This approach addresses problems with count-based metrics by focusing on boundary-to-boundary traversal within polygons, ensuring a direct comparison between ground truth and prediction. The research concludes by defining a pedestrian graph and a polygon graph, highlighting the importance of terminating nodes and their intersections with boundaries. The concept of polygon traversability is defined as a pair of boundaries, G, I, G, J, being traversable in G if there exists a pair of nodes, U, V, such that U is reachable from V in the polygon graph SG. The traversable boundary pairs of G and G are denoted as traversable pairs, G, G. A traversability metric is proposed, which compares the sets of traversable boundary pairs for a polygon from each graph using Jacquard similarity. This metric is essential in evaluating the performance of pedestrian graph prediction models, as it captures the difference in global paths between the predicted and ground truth graphs. The implementation of traversability involves partitioning the entire test area into tessellating intersection polygons, TIPs, which are created by assigning a point location to a road intersection and computing the associated Voronoi polygons. This approach enables the efficient computation of local connectivity metrics, such as betweenus centrality. The authors conduct experiments on segmentation assessment with multiple inputs, including aerial satellite images, street map images, and both. The results show that using both inputs improves the segmentation performance, particularly in removing spurious predictions and recovering occluded sidewalks. A quantitative analysis of the performance at the graph connectivity and routability level for different methods when testing in different cities is provided. Additionally, the authors evaluate the routability of the predicted graphs using graph-level metrics, including local and global metrics. The local metrics include average connected components, average betweenus centrality, and traversability similarity. The global metrics include node count, edge count, and average degree. The evaluation results are summarized in Table 2, which compares the performance of different methods, including tiled 2net, pedestrian-Inferred, and profit with various backbones. The results demonstrate the importance of using graph-level metrics in evaluating the performance of pedestrian graph prediction models. The PathwayBench benchmark offers a comprehensive evaluation mechanism for extracting pedestrian pathways from aerial imagery, addressing inconsistencies in datasets and metrics used in the literature. It includes 5 co-registered features and a suite of metrics tailored to assess the structure of the graph, ensuring routability properties for downstream applications. The evaluation focuses on the experience of travelers, highlighting strengths and limitations of existing methods obscured by conventional pixel-wise evaluations and simple edge counting approaches. The profit models, particularly those utilizing the VIT architecture, show better performance in graph routability, achieving the highest traversability similarity values among the evaluated models. This finding emphasizes the importance of considering how travelers navigate the environment, as the F1 score alone may not reflect practical requirements for real-world routing and navigation tasks. The PathwayBench benchmark is designed to catalyze advancements in the extraction of large-scale pedestrian pathway networks. The research on high-definition maps and road network extraction from various sources, including remote sensing images and crowdsourced GPS data, is presented. The HD Map Gen model generates hierarchical graphs of high-definition maps, while studies on sidewalk extraction use aerial and street view images. Road network extraction from VHR remote sensing images is also discussed, utilizing OpenStreetMap as benchmarks. The importance of unbiased datasets is highlighted, and the need for predictive equity in object detection is emphasized. Additionally, the creation of annotated datasets for learning urban pedestrian path networks and collecting sidewalk network data at scale are discussed. The FUNet network is introduced, which fuses location data and remote sensing imagery for road extraction. This research showcases the advancements in creating and utilizing high-definition maps and road networks, highlighting the significance of diverse data sources and unbiased methodologies.